All right, we are back. So let's prove that CNFSAT is NP hard unless there are other questions.
Let's do an NP easy first.
There are called NP intermediate problems. So that's it. There's a theorem called I think it's called Latiner's theorem or something. That if P and NP are different, then there are some problems that are neither NP complete nor are NP. So it's somewhere in the middle. Yeah, it's a really cool theorem, but obviously we don't know if such a thing exists.
Out of curiosity, does NP hard have anything to do with like the relation, or is that, or the relationship to difficulty, or is it just like a name they gave it?
It means at least as hard as NP, intuitively,
Okay.
but formally it just means any problem in NP reduces to it.
So it's like a lower bound?
Yes, yes. Supposedly, if P and NP are different.
Yeah.
Yeah. Other questions? Okay, so we don't have an NP complete problem to work with, so we need to prove that this one's NP hard by showing that any problem in NP can polynomial time reduce to CNFSAT. So let B be any language in NP. Well, by definition of being an NP, there exists a non-deterministic Turing machine, let's call it T, for B, that runs in, well, I don't know the polynomial that it runs in, but it runs in some polynomial, so let's call it poly of n time. And let's fit in the constant too. So the idea that we came up with is we want the answer of the reduction to be the same. So if we want an input string W to be in the language B, if and only if whatever formula we construct is true or is satisfiable. And if it wasn't in the language B before, it's not satisfiable now. So the idea we came up with is let's look at a simulation of whatever Turing machine T on input W. And what we want to do is look at that simulation and build a formula off of it that verifies that the simulation was correct. So the formula is true if if every single step is a valid transition of a machine and it accepts at the end. Okay? So what we're going to do is, so I'm just going to write it down here, build a formula that is satisfiable if and only if the original input was in the language B, or T accepts the input W. Okay. So, how did we verify that a computation really was correct before? Well, what we did is we saw, was the very first step the start configuration? And then we also verified that the last step had Q accept somewhere in that string. And then also we wanted to check for every consecutive steps, did it actually do a valid transition of the machine? So that's what we're going to do here. We're going to make a formula that makes sure that the first step is the start configuration. Make a formula that makes sure that the last one is some accepting configuration, and every single step yields them one right after. So let's see. If this machine runs in poly n time, how far to the right could I go in principle? Well, I can only move one step to the right every single time. So at most, I can hit poly n size. Sorry, poly n tape cells.
Because C sub n is the final of something.
No, because I know it runs in poly n time.
Okay.
So I can't hit further than that cell. Okay? So a common way to prove this, that this is not what we're going to do exactly, but it gets the idea going. So we're going to look at what is called a tableau. And what it is a giant grid that is basically what the simulation looks like. So we're going to make a giant grid. I'll tell you the size in a bit. And what this is it has number signs on the left and right sides, all the way down. And the cells in the middle are the actual computation. So the first row better have the start configuration. So the cells are going to look like Q0, W1, W2, W3, up to Wn. And since this is a grid, I may have some cells to the right that are blanks, because I'll need them eventually maybe in a further step. So I'm going to put blanks here all the way to the end. If I put blanks on the end of the configuration, that doesn't really change anything. It just makes the configuration longer, but it doesn't change anything.
And so these are automatically made to be the size of like the maximum.
We're going to force it because I know how long the machine runs.
Okay.
So this is not an explicit conversion, but I know it's like an existence one. I know that it runs in that amount of time. And then we're going to force this grid to be that size. Okay? Cool. Well, and then the next step is going to have whatever it does after one transition. The next one's going to have what it has after two transitions. And then hopefully at the end, I see a Q accept somewhere. So as I said, this is not what the formula looks like. It's just a grid, but it gets the idea going on how we could verify this. Okay? Cool. So let's see. How long is this grid? Well, I know how many steps the machine took because by assumption it took poly n steps. So the height of this guy is poly n. And like we said, we can't access the poly nth cell or later than the poly nth cell because we can only move one step to the right every time. So I know that the furthest right I can go is poly n. So the whole thing is poly n in size 2. So it's a square grid, but that won't actually matter. And what we want out of this grid is make a formula based off this that is satisfiable if and only if the Turing machine from before, T, accepts that string W1 through Wn. Okay? We want a formula that basically can encapsulate what this computation is doing and be satisfiable if it is a valid accepting computation. Questions? Because the ride just started. All of the steps that we're going to do right after this are very intuitive, but they have a bit of detail, so don't feel bad if you don't understand it the first time. Look at how each of the steps is going to go, and relook at it if you need to. Okay. Well, we need something that represents variables and clauses. And how are we going to connect everything up? Well, we want a formula for the start config. We want a formula for end config. Sorry, not end. Accepting config. And we better sure the start config is in the first row and accepting config is in the last row. And then a formula to make sure each row yields the next. And I'm going to number these 1 through 3. I think we'll need more than that. Yeah, we'll need one more than that. Yeah.
So when you're saying the formula for accepting config needs to be in the last row, does that automatically mean it's going to be in that poly n?
Yes. Mm-hmm.
Okay.
So we're going to have a variable that will work with the poly nth row.
So that just means that it's when you're saying like the poly nth row, that's just the amount of space that particular one needs, right?
Yeah, whatever the last row is. Yeah.
Okay.
Yeah. Or really the last step, because we're not really supposed to think what a Tableau is, but it gets the idea going. Because we're thinking row here, but it really means the step.
I was just trying to make sure we're not forcing it to be like some maximum size, you know.
Well, I know how long it runs, so I'm just forcing it to be that. Because I know it runs in that amount of time by assumption. Mm-hmm. Other questions? Okay. Well, look at that first row. Can I have anything other than Q, ignore the pound sign, Q0, W1, W2, W3, all the way through Wn? No, I must have exactly that. So maybe what we can do is look at each of the cells and make a variable that represents you're in that row, that column, and you have that value. Okay? So like for example, the first row, first column better have a pound sign in it. And the first row, second column better have Q0 in it. First row, third column better have W1. And all the way through the rest. Yeah.
How much does this relate to our homework problem? The thing with the characters, with the regular expression.
Nothing.
Okay.
Yeah, this has nothing to do with the homework. Yeah, because we're making variables here. So what we're going to do is make a variable. We're going to call it X, I, J, and L. So it's going to have 3 subscripts. Where I is any row. So for example, I runs from 1 to poly n. J is any column. And same thing for the bounds. And L is any of the symbols. So let's say that there are S symbols, tape characters, states, and pound sign. Because we gotta represent pound signs and states in each of the rows. Okay, so we're gonna make a variable that represents in row I, in column J, you have the value L. Well, could I, in principle, have a the formula that I'm going to make that could have xijl and xijl bar, L prime, let's say, where they're not the same value. Could I have both of those be true?
Repeat that one more time.
Yeah. So if, I'll just write it here. Could both xijl and xijl prime with L not equal to L prime be true? Both true. Well, in principle, they could be, but do we want them to be both true? No. So we want to have a formula that says you can't have two different values in the same cell. But can I have zero values in a given cell?
No.
No, I must have something there. Yeah.
Does the space count as a value?
Yeah, it's a tape character. Mhm. So we gotta have a formula that says you must have at least one value and you can't have two different ones. So let's make that one. So we're gonna call it phi sub cell. So this formula is gonna be true if and only if every single cell has exactly one value in it. Okay? Well, does this formula have to work over every single row and every single column? Yeah. So we gotta do a giant AND over every single cell. So let's do one giant AND over all of the rows and one giant AND over all the columns. Because this formula better be true for every single one of the cells. Okay. It gets worse. Don't worry. Well, how do I depict, so I've now fixed a given row and a given column. How do I say at least one of the values is there? Well, it could be the first one, or the second one, or the third one, all the way up to the nth one.
You mean one of those values must be.
Yeah, one of those variables, x, I, j, some value is true. Well, what I can do is whatever it is for the first value, or whatever it is for the second value, or the third one, or all the way through. One of those must be true. So let's do an OR over all possible values over the possible variables. So as is, this says, if I just close this off right here, which I won't for now, but this is true if and only if at least one value is in every single cell. Because like for some row I and column J, if no value's in there, like all the L's say no, we're all false, then this AND will take care of it and say the whole formula is false. Okay, so we must have at least one value in each of the cells. But now we gotta take care of the problem of having two different cells. Two different values in the same cell, and we don't want that to happen. So we're going to AND this with something else. Well, what we want to do is, for any two values that are different, it can't be the case that this one is true and this one is true. But another way of saying that is, it can't be the case that not this one or not this one are true. So, giant AND over all possible pairs of symbols that are different. So this says for all possible pairs of different symbols, we want to have that you can't have both of them at the same time. Okay? If I have both of them at the same time, I want this and to be false. And so if I make this and to be false, then the whole formula is false, which is what I want. So we don't want xij sigma 1 or xij sigma 2. Okay, so let's recap what this whole formula is doing. This is not the end formula. There's much more. Yeah, this is a long proof, but at least it's intuitive in this case. We want every single row and every single column, you want exactly one value in that cell. So we range over every single row and every single column. In each one, we want at least one value, which is what the first one says, and we can never have two values in the same cell. And we say that by, we look at every pair of symbols that are different, and we say, you can't have either one of these. Well, if we did have both of them, then their value is true, which means I will have a false or false. But false or false, that is false. And so this giant and here in the center, that will be false. And so now the whole formula is false.
Can you do an example of the latter part with the and with an example from the Tableau?
Yeah, sure. So if I have, let's do a zoom in here. So if I have $Q0, W1, and I don't care what the rest is, then this guy right here will be, let's say those are the only three symbols, for instance. It's not, but let's say that that's what is true. Then we'll have X1, 1, $, can't be $, or X1, 1, Q0. Then and with other stuff. Yeah, so if we wanted to put $, and Q1 into that same cell, then if we look at this and say that those two variables are true, their negations are both false. And so then the disjunction or of two things that are false is false. And so this and over all the pairs of symbols that are different, that will be false. But that was anded inside this whole thing, and so the whole formula will now be false. So I can never have two things being in the exact same cell. Okay? I think this is the worst one. Yeah, that's the worst one. Yeah.
So far we have the first part saying each cell has at least one value.
Yes.
And the second part saying it has at most one value.
It can't have two, but yeah, that's at most one.
Okay.
Mm-hmm. Yeah, so that'll force exactly one value. Okay, other questions? Okay, so now we want a formula for start config. So we want a formula that is true if and only if we started off correctly. Okay? Well, what must be in the first cell, first column? First row, first column? $. What better be in the first row, second column? The start state Q0, then W1, W2, W3, all the way to Wn. Then what must appear afterward? Blanks, and then what's the very last one? $. So let's make a formula that does an and over all those variables. So we call this phi start. So that says we must have X1, 1 $, and X1, 1, X1, 2 Q0, and yeah. So now I'm just going to do gigantic and over all of the symbols in WI. So giant and, let's say it has n characters. Then we want x1 I plus 2 because we shifted it by 2. WI. So before I go on, the first one says you must have pound sign in the first row, first column. Then you have Q0 after that. Then you must have WI. You must have WI in position I plus 2 in the first row. So W1, W2, W3, all the way through WN. Then what must appear afterward? Blanks until what value? Poly n, yeah. So it's actually poly n minus 1, but we can ignore that. So, and, well, I better start, I'm trying to make the variables intuitive. Let's put I equals n plus 1 to poly n. Then we want x first row, then the ith column to be the blank symbol. Actually, I'll put minus 1 here, poly n minus 1, to make the bounds work. Then we want the very last one to be, so poly n here to be pound sign. So we must start with pound sign, Q0, then W, then a whole bunch of blanks, then pound sign at the end. And so clearly that formula is true if and only if those variables are true, because it's just a gigantic set of ands over everything. Okay? Not much more. So, yeah.
Why would those eyes not be J's?
So that was the thing I was debating. I should call these J's, but the name of the variable doesn't matter. I was thinking, should I use J, but then I realized I messed it up in the middle, so yeah. Yeah, it's just a name. Well, we made a formula that checks if the first row is okay. Now we need to have a formula that checks if the last row is okay. Okay, so we need a formula for except config. This one's actually the easiest one. So we'll call this phi except. Well, do I care what is in the last row other than the fact that there's a Q except somewhere? No, I don't care. So it could either be the first guy be Q except, or second guy Q except, or third one Q except, or, so how do I do this? Just do a gigantic or over the last row. Okay? So I will do J this time. So I'll do J to be 1 to poly n. Actually, I should do, it actually won't matter here. I was thinking I should start off at 2 because I will always have a pound sign there, but the formula to check if 2 rows, one yields the other, that'll take care of this anyway. So those variables will never be true. Anyway, we want that the last row, which is poly n, and column J, one of them at least has Q except in it. Okay? So we're almost there, I promise. So let's just recap what we did in total. We made a formula that checks if we have exactly one value in each cell. And then we checked, do we start with the start configuration? Do we end with with some accepting configuration? What do we need to check now? Formula if every single row yields the next one. Okay? So this one we're not going to detail all the way, but think about it for a second. If you have one row that yields the other, how many places could they be changed? Very few. Well, I could either move left or move right. Well, I'm only dealing with 2 rows right here. How many columns? Well, the one I was at, and potentially going left, potentially going right. That's 3. So we need to look at what is called a 2x3 window into your soul. All right, so yeah, so we're not going to look at this completely thoroughly, but because it depends on the Turing machine itself, because it looks at the valid transitions of the machine. So we're going to define phi legal I j to be true if and only if row I yields row j. And I think the book has a detailed explanation of how to approach this, but the idea is, well, you're going to look at all the 2x3 windows given 2 rows, and you're just going to check for all the possible 6 combinations that there could be, is it a valid transition? Well, other than where it could possibly be different, they must be the same, because I can only make a transition in one place, right? So most of these are going to be, it's going to have 3 identical things in the 2 rows. But where they're different, we just need to look at the non-deterministic machine and see whether it's a valid transition. So I'm not going to detail this formally, but it's intuitive how we would actually do it. Well, how would I check that every single row yields the next one?
That window has to be centered, because the first row has to be centered over your last use case, right?
But I need to make sure that it, like, somewhere else it didn't like change a symbol.
Oh, yeah.
Yeah. So I need to check it for every 2x3 window. So how would I check that every single window is valid? Well, I look over every single row and every single column. So we're going to say phi sub, how do I call it? Move to be, so I want this to be over, so the bounds are going to be slightly different. I want the rows to go all the way until the second to last one, because I don't need to do this for the very last row. And then we want, so then we want j to go from 2, because we don't need to look at the left column. To go to poly n minus 1 as well, of phi legal ij. Last one, I promise. So you can look in the book for how this is formally done. But the idea is that we just look at every 2x3 window, make sure it's a valid transition of the machine. If it's valid, if we check the transition within 2 given rows, then the rest of the 2 rows must be exactly the same. Okay, well, now we've actually verified whether the computation is accepting. It has exactly 1 symbol in every row, but we start off correctly, we end correctly, and every row yields the next one. So we want all of those to be true, so just and over the 4 formulas that we just made. So make phi to be phi sub exactly 1 thing in every cell, and we start off correctly, and we accept at the end, and every transition is valid. Every 2 rows are valid. Well, finally, we're done. So this formula must be true if and only if the original Turing machine accepted the input, because each one of these is captured by the Turing machine that actually computed on that input. So phi is satisfiable if and only if that machine T accepted W. Can I now claim that CNFSAT is NP hard? Well, to be NP hard, you must be polynomially reducible from every other problem. Was this a polynomial time reduction? Or did I take longer than polynomial time to make this guy? Well, let's check, just to be sure. Did phi sub cell take more than polynomial time to make? Well, there are polynomially squared number of ands out there, and if s is constant, then there's only a constant number of things inside, so polynomial, fine. Phi sub start, that's clearly polynomial because it's only one row. Phi accept, that's only one row, again polynomial. And phi legal ij, well, each one of them is polynomial for each two given rows, and phi sub move is just more polynomials on top of that, so that's just still polynomial time. And to make the final formula, you just put a couple ands in between. So therefore, I made this formula in polynomial time in terms of the size of the original input. Okay? So I can now officially claim that CNFSAT, finally, is NP hard. Don't worry, none of the other proofs are this hard. But we needed to get off the ground somehow. Okay? I could just make the final exam reproduce a proof like this. No, I won't do that.
Reproduce?
Yeah.
This is what you get for not coming to class.
Yeah. And any questions on how that was made? There are a lot of details, but the intuitive idea is that we're just simulating the original machine as a formula. Any questions? Okay, so let's prove some other problems hard. So let's go back to that CLIQUE problem that we were talking about earlier. Well, what are the two things I need to check in order to show that CLIQUE is NP complete? That it's in NP and NP hard. Did we show one of those already?
We showed that
That there is a verifier for CLIQUE. So what can I claim now? That's an NP. Good. Perfect. And then now we just need to show that CLIQUE is NP hard. And if we have to go through a proof like that again, I don't want to teach anymore. So is there an easier way to show that this is, or any other problems now, NP hard? Well, yeah, we could use CNFSAT to help us. So the idea here is, if everything reduces to CNFSAT because it's NP complete, well, if I can show that we can turn CNFSAT into CLIQUE, we're done. Okay? So we need to show that CNFSAT poly reduces to CLIQUE. Because CNFSAT is NP hard, is NP complete, but rather is NP hard, CLIQUE, if I can show this, is also NP hard. And then therefore we're done. Okay? So what do we want? Well, we got to turn this thing that looks like variables and clauses into something that looks like a graph. And we have that the original formula is satisfiable if and only if the graph that we make has a some number clique. And we get to choose k at the end. Okay? So let phi be a CNF formula. Let's say with n variables and m clauses. So what we're going to do here is what is called a gadget proof. We're going to make a couple vertex gadgets, and we're going to connect them up in some intuitive way. And gadget proofs are used a lot in NP completeness proofs. But how are we going to proceed here? Well, suppose that I gave you an assignment to the variables. For each of the clauses, how many of them must be true in order for that clause to be true? Just one. I only need one of them to be true. Let's try to make that one of the vertices in the clique. Okay? So we're going to have to design it so that the variables in the clause correspond to, if you pick one of them to be a candidate for that clause to be true, that is a candidate in the graph that we'll make that will be a clique, part of a clique. So it's like what is called the witness of the clause to be true. It's the witness of the witness for the vertex to be in the clique that we're going to make. Okay? So let's see. For each of the M clauses, make a what is called vertex gadget. So let's say that it is equal to x1 or x2 or xn, let's say. And then we're going to make the vertex gadget be a bunch of isolated vertices. This thing doesn't have any cliques in it, so we got to eventually add edges. But for every one of the clause, we're going to make an independent copy of something called a vertex gadget. So if we have, let's say, x1 or not x2 or x3 and x1 bar or x2, then we're going to have a vertex gadget x1, x2 bar, x3, and then we're going to have another one over here, x1 bar, x2.
Purely just
Yeah.
iterate the
Yeah.
vertices.
Just have a bunch of isolated vertices for now. But we're going to add a bunch of edges in a bit. Well, let's see. I only want to pick one variable out of each of the clauses. I could pick more, but if I can suffice with picking one, we're already good. But could let's say I pick x1 in this clause. Could I pick x1 bar somewhere else as its witness? No, because that can't be, yeah, if I pick that witness, that guy is false. So therefore that clause wouldn't be true. So we're going to have edges to be all the valid connections. Okay? So we're going to connect vertices, we're we're going to connect all pairs of vertices if and only if they are not in the same clause, nor are they complements of each other. So like for the graph above, I should make an edge between x3 and x1 bar because they're not in the same clause, they're not in the same clause gadget or vertex gadget, and they're not complements of each other, of the same variable, I should say. Not each other, I should say the same variable. And here I should make a connection between x2 bar and x1 bar because they're not in the same clause and they're not the same variable negated. But should I make a connection between x2 bar and x2 over here? No, because those can't be in the same clique, whatever clique that we're going to make. So if I make all the other connections, let's see. Yeah, that's it. Nice. Well, if I pick one variable out of each of the clauses, how many variables will I make? Or select? Well, no, if I have m clauses and I pick one variable for each clause, how many variables did I just pick? M, right? Well, what should I have at the end? An M clique, or a graph that has an M clique, because I picked one variable per clause. So our claim then is the graph has an M clique, which is the number of clauses in the original formula, if and only if the original formula is true, it is satisfiable. Well, let's make sure that we actually preserve the answer as we did in the reduction. Well, if the original formula is satisfiable, then I can pick some variable in each of the clauses to make the formula true. Well, as we noted, it can't ever be the case that it's some variable in some clause and the negation somewhere else. And we precisely made edges so that we avoid that situation. What about the other way? Suppose that this graph that we just made has an M clique, where M is the number of these vertex gadgets. Well, there must be some vertex in each of the gadgets that we select because there are no edges among them in the same gadget. So if it has M different vertex gadgets and we have an M clique, we must have exactly one in each of the parts. So now just in each of the corresponding clauses in the formula, pick that variable to be true, whatever the clique happens to be. So, for example, does this graph that we just made have a 2 clique? Because there are 2 clauses. Yeah, it has a whole bunch of them. So let's, for example, look at x3 to x1 bar. So what would I have? So in the formula, that says set x3 to be true and x1 to be false to make x1 bar true. Well, let's see what happens. x3 true, well, that makes this first one true. Well, setting x1 bar to be false makes the other one true. Okay? Come up with what? Because I selected that edge, because there's a to clique, which means an edge. So if I look at the endpoints of that edge, which is x3 and x1 bar, that means in the original formula, set x3 to be true and x1 to be false. Yeah, so the bar just means pick the negation. I could have also picked x3 to x2, which means setting x3 to be true and setting x2 to be true, which also makes the formula true. Okay? So this is a valid reduction. Is that what I needed to show, though?
We have to do it for K.
Yeah, but I pick my value of k when I make the graph, which happens to be m in this case. Well, what else do we need to make sure of in this reduction? Just like we checked before, does this reduction take too long? Or does it take polynomial time? Well, let's see. How big is the graph that we make? Well, there's a vertex for each of the instances of the literals, which is polynomial in the size of the formula. How many edges are there? Well, there could be a whole bunch, but it's at most quadratic the number of vertices that we have, because we can't have more edges than that anyway. So that's polynomial too. So the graph is constructed in polynomial time in the size of the formula. Okay? Any questions about that?
Somewhat trivial question, but were we setting it so that x1 bar evaluates to true, so x1 is false, or we set it
Yeah.
so that
So the original, one of the original assignments to make the formula true is x3 to be true, x1 set false.
okay, x1 set false.
Yeah,
Okay.
yeah, is an assignment to make the original formula true. Other questions? Let's do a fun one. So I'm gonna